Hello everyone, Mr. Geidel here. I want to go through some of the materials for studying for the forces quiz there. I won't be in class today, as I'm sure you know, so you can use this kind of video key to look at all that. The first thing is the review set, the problem set that we started in class. I'm just going to go through the whole thing here so that you can review it if you need it. 60 gram tennis balls fired. What's the net force on the ball? Okay, I find the net force by summing up the forces. Okay, but there's also another way. Right, F equals ma. Right, and I noticed that I have some kinematic stuff in my problem. So the fact that it leaves at rest is a kinematics variable too. So if I can find an acceleration, okay, I can use Newton's second law to find the force. I can't go this route though, right? Because I don't have a time. What I can do is look at a kinematics chart. All right, and this is from rest to when it leaves the barrel. So I don't know, to y equals 1.5 meters, which of course is a displacement. It said the ball starts in the device at rest. It's going to end at 12 meters per second. And I'd love to know the acceleration so I could plug it in there. Well, there's only one kinematics equation that doesn't rely on time, and that's this one. Okay. That's kind enough to be 0 for us, right? And we can rearrange for what we want. U squared over 2a equals, solving for a equals a. I got my 12 meters per second over 2 times 1.5 meters. Let's say 12 squared is 144 divided by 2 divided by 1.5. They should get 48 meters per second squared. Okay, but of course I'm not done. I wanted the net force on the ball. So I got my 0.06 kilograms, right? Got the point 1, 2, 3. Right, 1, 2, 3, that's right. .88 newtons is the net force. The device itself applies 5 newtons of constant force while firing. What's the average force of friction? Let's look at that other definition of the net force, right? We know we find the net force by summing up the forces. Okay? And yes, that's equal to ma, but we actually just found a number for the net force. So whatever the forces sum up to, it's going to equal 2.88 newtons. Right, that's our number for ma, which we just happen to have. So we do this positive forces minus negative forces. We're firing straight up. We'll make our math teachers proud and call that the positive direction. So the device applies a force up. Friction combats that, and so does weight. And I'm solving for the thing I want. Okay? So what I can do is, I can add friction over and then subtract the net force over. So friction equals the force of the device is 5 newtons. The weight is our, 0.06 kilograms times, 10 meters per second squared, so that's 0.6 newtons. It's not super heavy. Minus our net force. Force of friction is my 5 newtons minus my 2.88 minus 0.6. Should get 1.52 newtons. Now the device is laid at an angle, but it's fired at 12 meters per second again. Okay, so that's no longer straight up, it's at an angle, so it's two-dimensional. The ball lands 13.6 meters away from the device, so if you imagine my little potato cannon, tennis ball cannon type thing, I'm going to shoot at 12 meters per second, okay, and it's going to land 13.6 meters away. That's a horizontal displacement. And I have the flight time too, so if only I knew how much of that velocity was in the x direction in business, okay, because I could use that side to find my angle. So I know horizontal motion is uniform, no acceleration, so I get to use this guy, okay? And if it scooched over 13.6 meters over the course of 1.3 seconds, the horizontal component of that velocity is 10.46 meters per second. And now I have an adjacent, right? To my unknown angles perspective, I just found the adjacent, and what will relate this adjacent to that hypotenuse will be cosine. Right? Adjacent and a hypotenuse, I want cosine. Cosine of my unknown angle is my adjacent over my hypotenuse. Okay? I don't want cosine of theta though. Right? I want theta. Right? If I do the inverse cosine of the cosine of theta, those will undo each other, right? And it'll leave me theta equals, okay, what happens on the right is I get something that can go in my calculator. And I go into my cosine menu. I don't want cosine, I want inverse cosine of 10.46 divided by 12. I get 29 degrees. And I should kind of interpret that, right? That's 29 degrees above horizontal. Let's describe the difference between kinetic and static friction. How do they compare? Okay, well, kinetic, think kinesthetics, right? Work those word roots, right? In kinesthetics, there's movement. Okay, so these are when two surfaces are sliding relative to one another. Static friction is when there is no relative motion. Okay, maybe there's motion trying to happen, and it's opposing that. Static friction will be greater, right? For any combination of surfaces, static friction will be greater, and the same can be said about the coefficients. The other thing is, well, our friction formula, when we use it on kinetic friction, right, that gives you the value of kinetic friction. But when it comes to static friction, we need to remember that it's this formula gives us the maximum, right? So the friction is actually less than or equal to this. Okay, I have an object that's sitting still. There's no static friction there, right? It's when I go to push it, static friction happens, right? The microscopic, things are made of molecules, and those interactions, the surfaces are jagged and rugged, and the intermolecular bonds tug on each other, and the electron clouds repel each other, and all this fun stuff that when we talked about contact forces, we explored a little bit. That's all happening. And eventually, if I exceed this force, right, the static friction will get bigger and bigger and bigger, and if I overcome that, then I have unbalanced forces and motion happens, and then I instantly switch to that. So that's what's different between kinetic and static friction in a nutshell. Why might a person standing on a bathroom scale in an elevator see a reading that is lower than their actual weight? Well, imagine, I'm standing on a scale, and the scale pushes back with the normal force. And if I'm just in my bathroom, okay, there's no acceleration. If I sum up my vertical forces, that's going to equal 0. So my positive force minus my negative force must be equal magnitude. Um, so how could that be different? I'm not going to change gravity unless I go to a different planet or change my mass. Okay, but the normal force can change, which is actually what the bathroom scale is reading. So when might the normal force be lower? Well, if that was the case, my free body diagram might look something like that, right? And I see that I have unbalanced forces downward. So if the elevator were accelerating downward, the scale would read lower than my weight. Likewise, vice versa, if I'm accelerating upwards, my apparent weight, normal force is kind of like our apparent weight too, um, that would be higher. The scale would read higher. Alright, let's look. Philip and Enrique are pushing on boxes, okay? If Philip pushes to the north, that's supposed to be an arrow to the north, with 600 newtons. Enrique pushes west with 650 newtons. What is the magnitude and direction? Well, the magnitude of these two forces at an angle will be, I can use Pythagorean theorem to find, I know my alphabet, I promise. And it doesn't really matter who's the A side and who's the B side, as long as the hypotenuse of this triangle is C. That's what's really important. Do that. I got C squared. I can take that, but I don't want that. I want the square root. So 880 we'll call 5 newtons. So that's the combined effort of both boys. That's the net result. Okay, and now the direction, I don't know, let's pick if I wanted to do this like a compass bearing, right? That angle there would be my compass bearing. I don't feel like I need to do that. Any angle will do. If I did this angle, this is how, because that's kind of the direction. This is how west of north I am, right? If this angle is 0, I'm perfectly north. If this angle is 90, I'm 90 degrees west of north. I'm perfectly west. So we could say that. We'll put this in terms of how west of due north we are. And again, I'll take whatever is, mathematically equivalent to what's happening. But I can go back to my triangle, right? I have sides. Trigonometry will help us relate these sides to unknown angles. The problem gave me an opposite and an adjacent. So let's run with tangent. Tangent of any angle is the opposite side, and here the 650 is opposite over adjacent. Okay, newtons will cancel. I don't want tangent of theta, I want theta, so I'm going to take inverse tangent of the left and the right. And on the left, tangent and inverse tangent cancel and give me, theta is, which is what I want, and the right is something that can go in my calculator. .47 degrees west of due north. Good. And if I wanted the other angle for some reason, it'd be 42 degrees. I don't know, what would you call that? South of west, or it'd be north of west. 42 degrees north of west. Keep it simple. Alright, if I do want to make my Boy Scout Cub Master happy and use a proper compass bearing, that whole circle's 360. So if I had 360 degrees minus my 47, it's like a compass bearing of 313. just pretty northwest. Now Philip pushes north with 600 newtons, but Enrique pushes south with 650 newtons. What's the magnitude and direction of the net force? Well, just look in here. Hopefully you see that the direction will be south, right? These do lie in the same dimension. They're both in the north-south dimension. So I don't need any trigonometry. I could just get to add these algebraically, right? When forces are in the same direction, they add. When they're in the opposite direction, they subtract. And if they're at angles in between, that's when I use trigonometry. These I just get to subtract, right? They're 50 newtons is the unbalanced portion when they cancel each other out, right? And that, of course, is south. Philip pushes north with 600, and Enrique pushes north with 650. Well, now they're working together, right? And these will add up, right? They'll add up to 1250 newtons, and of course, that's north. If the mass of the crate in question 4 is 100 kilograms, what are these accelerations? So up here, F equals ma, so of course the acceleration is F over m, right? We're ignoring friction here. So the boy's force is the net force. What was I got rid of my acceleration. What was it, 850? Gotta look through it in I'm still in pen mode. 885. Okay. So I had a force of 885 newtons applied to a 100 kilogram box, right? So whoop, whoop, I'm going to get acceleration of 8.85 meters per second squared. Sorry. Remember, a newton is a kilogram meter per second squared. So when I divide this, a newton per kilogram when I divide kilograms. So that's helpful to remember. Here, 50 newtons south, right? I've already rearranged Newton's second law. A net force of 50 newtons on my 100 kilogram box will be right, and then in C, same thing. Good. I did it right. An object sits on a desk. Why doesn't it accelerate downward due to gravity? What contact force is at play? Why does this happen? Okay, well, because gravity isn't the only force, right? When the object goes to accelerate downwards, its molecules interact with the molecules of the table, and the molecules of the table are held together with intermolecular bonds, and those bonds kind of act like springs, and there's tension in those bonds, and they push back, right? So we call that a normal force. Right? Surfaces don't like getting pushed into, and they will push back, right, with a force perpendicular to the surface. And that's called the normal force. The nature of the force is intermolecular bonds don't, act like springs, and the molecules don't want to get ripped apart. If my object gets big enough, I guess I could break the table, and then I'll accelerate to the ground, till those molecules hold me up. All right. Cool kid leaning against the post. Okay. That's my cool kid leaning against the post. Okay. He needs sunglasses. He looks cooler without glasses. Backwards hat. Okay. Same thing. Okay. And in class, someone mentioned just friction, static friction. I mean, that's a thing, right? You ever leaned against the wall and slipped, right? But friction prevents motion between two surfaces. So, maybe friction might stop him from sliding down the wall. Okay. But what holds him up, what holds the lamp, is pushing back with a normal force. I know we see normal force pointed upwards in a lot of our problems, but that's not the rule. The rule is it's perpendicular to the surface. So if I'm pushing against the vertical surface, it's going to push back horizontal, right? As long as the surface and the normal force form 90 degrees. What is inertia? Well, it is an object's tendency to resist changes in its motion. All right, inertia is laziness. So when when an object is pushed or pulled with a force, right, its change in motion, because that's what acceleration is, right? The rate at which kind of your velocity changes, and velocity is a really good description of your motion. It's the inertia, the mass. That's the second part of the question that will determine how much your motion changes for a given force, right? And that's actually what you measure, right? You want to measure an object's inertia, you measure its mass. The more stuff in an object, the more it resists changes to its motion. A 200 kilogram wooden box is sitting motionless on a wooden floor. There is friction between the two. What is the box's acceleration if a person pushes with a horizontal force of 700 newtons? Well, if I want to know acceleration and I'm given information about forces, I am probably setting up Newton's second law. Okay, if I did a quick free body diagram for the box, it's on Earth, and Earth will pull on it. I don't see boxes accelerating into the ground very often. Perhaps, I'm applying a force, and friction's, gonna combat that force. The acceleration lives in the horizontal direction, right? And that's just from the problem itself. I'm pushing horizontally. You've pushed things before, okay? You don't need a formula sheet for that, right? You push something horizontally, it's gonna move horizontally, ostensibly, right? So since the motion is going to be in let's start with the horizontal direction. Let's sum up forces in the horizontal direction, and if we run out of information, we can sum up forces in the vertical direction. Well, so we established that to find the net force, you sum up the forces, right? And of course, the net force is equal to ma, according to Newton's second law, and yeah, we're in the x direction here, so we'll do that. We'll sum up the x forces. Let's say the applied force is the positive one, and friction opposes it. Okay, so we get a statement like this, and the question says, what's the box's acceleration? I could rearrange for this. Right? I'll divide both sides by mass, and bada bing, bada boom. And I know more about friction, right? I know that the friction force is mu times the normal force. I have a wooden box on wooden floor, right? So I can go look up my coefficient with sitting motionless. So let's look at static friction, although as soon as it starts moving we'd use kinetic friction, but I want to show you something that's going to happen here. And I could even keep going still too, right? I also know there's not even motion vertically, let alone acceleration. So these will also sum up to 0, and if I did this quick, if I sum this up, that's 0. My positive force minus my negative force equals 0. So I can also state that I do know something about the normal force here. It'd be equal to mg. And so let's, I want to show you, you can have your reference table here, and you can look up the coefficients. Okay, wood on wood, right, has a kinetic coefficient of 0.3 and a static coefficient of 0.42. Okay, let's take a look at the static first, because I want to show you something. Okay, we're going to push on this. Alright, we're pushing with 700 newtons, right? So I got 700 minus something. And I like to leave things in variable form, but something, sitting motionless, what's its acceleration? I want to see something. And when I plug in mg, I get my 200 kilograms times 10 meters per second squared. So forgive me for jumping right to that. 0.42 times 2,000. So The static friction will actually go up as high as 840 newtons. Remember, this is actually an inequality there. Okay, it's 840 newtons. 700 newtons isn't even going to move it. So my acceleration is 0. If I found that this was less than the applied force, I would have some non-zero acceleration, and after an instant of non-zero acceleration from rest, I have non-zero velocity, and as soon as I have non-zero velocity, I have motion. I am using kinetic friction, so I would use my 0.3 for my coefficient and solve for acceleration using the equation we found. But this box isn't even gonna get moving. So when you see language like that, you know, it's not super physicsy of us, but perhaps your teacher's, a little metagaming here. Perhaps your teacher is asking you to consider the differences between static and kinetic friction. See if you're even going to move it first. Like here, the applied force isn't enough to even budget, so we can save ourselves some grief here. A 90-kilogram rocket man with 50-kilogram jetpack is burning up his fuse up there alone. Okay, so first things first, let's get a total mass. Don't even know if I'll need it, but let's just do it before I proceed and forget. The jetpack's thruster puts out 2 kilonewtons of force and is pointed 40 degrees below the horizontal. What is the magnitude and direction of the man's net acceleration? So if I was going to do the free body diagram for him, he's got weight, and then the thruster is pointing this way, and we talked a little bit about how stuff like this works when we did Newton's third law. The thruster's pointing that way, right? The jetpack pushes on the exhaust gas, and according to Newton's third law, the exhaust gas pushes back. So I'm actually going to get thrust that way. The thrust force points that way, and it is 2 kilonewtons, 2,000 newtons. Okay, and this here, I'll draw in my if I have 40 degrees below, those are actually vertical angles. Those are congruent. If you don't remember that from math class, you could still do this whole problem with this triangle here, and it'll be okay. It ought to work. But I want the magnitude and direction of the man's acceleration. So let's figure out. We're going to have to do this one bit at a time, because I have 2 forces, but some of this thruster is forward or to the right or whatever, and some of this thruster is up. This is the only horizontal force that'll be responsible for his horizontal acceleration, but I have 2 forces in the vertical direction, so I'll have to be careful and tread lightly as I go there. So let's split up the 2,000 newtons. Let's start with the force of thrust in the x direction, which that's an adjacent, so I'll use cosine, right? Cosine of 40 is my adjacent side over my hypotenuse. And I could cross multiply there and get that the horizontal component of the force is my 2,000 newtons times cosine of 40 degrees, which is something I could put in my calculator. Clacking of 40 degrees, 1532 newtons. Okay. Now my horizontal acceleration then, if F equals ma, right, a equals F over m. Okay, and I'm looking at the x component force, so I'll get the x acceleration. Right, it is the only x net. I'm waiting for the cat to come in, so I can close the door and letting all the bugs in. 1532 newtons to our 140 kilogram setup here. Get 10.9 meters per second squared. So that's my horizontal acceleration. Vertically, well, if the cosine gave me the horizontal component, then sine will give me the vertical component. It won't always be that way. I'll be honest, it will usually be that way, but as soon as you're on a ramp or you're turning, or there's a whole bunch of coordinate systems that's not true. So you gotta, I wouldn't memorize it that way. I'd memorize SOHCAHTOA, but one trig function will give you the horizontal and the other trig function will give you the vertical. So that is true. 1285. Okay, but there are other forces here, right? If I sum up the forces in the y direction, I get my we'll call that positive force, minus my weight. My negative force is the weight, right? And 140 kilograms times 10 meters per second squared is 1,400 newtons. He's actually dropping, right? I'm going to get a negative net force here. That just means this thruster isn't enough to keep him airborne. That's okay. Minus 1,400, negative 114. So I have a net force of negative 114 newtons, which is equal to ma, and I can solve for the acceleration. I'm dropping at a rate of 0.8 meters per second squared, which is fine. No one said it, it had to be going up, right? It's slowing his descent. So then I want the magnitude and direction. So magnitude, right, I find that I'm falling at 0.8. I am cruising to the right at 10.9. If I drew these tip to tail, my resultant would, the head of my arrow on the resultant would make a little more sense. Here, actually, let's just do that. Right, if I draw my resultant in there, the way it points makes more sense. The magnitude's the magnitude. That would have been fine, but here, I'm going to the right at 10 and down at 0.8. So now when I draw in my resultant, the head of the arrow makes sense. But hope Pythagorean theorem's Pythagorean theorem. Hello, Whiskers. Thank you for coming in. I appreciate that. Now we don't have to let all the bugs in. Good kitty. All right. I'm using Pythagorean theorem. And my negative here, I guess I could put it in there. It's going to get squared, so it doesn't matter. Magnitude don't care about none of that. I don't want c squared. Okay, so 10.93. Okay, so that's my magnitude. And now my direction, again, I could turn back to my triangle here. Okay, I just found an opposite side, right? Because that's my descending 0.8 meters per second squared, and I have an adjacent. Let's use tangent. The opposite was 0.8. I'll make it negative. It won't matter, but actually with tangent it might. Let's see. It should give me an acute angle either way. But let's play with it. Okay, I don't want tangent at theta. I want theta. So I'm going to take inverse tangent of each side. Oh, that goes there. And what I do to the left, I got to do to the right. So let me just do the magnitudes first. 0.001. But let's do it with. I wonder what we get when I put in the negative. We need like 4 quadrant tangent here. Yeah. Okay, that's fine. 0.001, right? My writing's in the way. Yeah. Okay. A very small angle. Okay, the horizontal acceleration is dwarfing this, drop, but I am dropping. My acceleration is pointing 0.001 degrees below horizontal. So I am losing height here. Alrighty. Yep. Did that. I'm still checking some numbers. Yeah. Alright. Ginny walks 200 meters east, 400 meters north, 150 meters south, and then 175 meters directly southeast. Okay, when we add a bunch of vectors, we have this other analytical method that's handy. And when we add vectors that aren't at 90 degrees to one another, we have to use this analytical method. Right? We know that when we add two vectors, or four vectors, right, the answer, the x component of the answer, will be the sum of all the x components. The y component of the answer will be the sum of all the y components. So you should recognize this. We did that little PhET sim, and this is how we did this. Let's whip up a coordinate system. We've got our compass rose. Okay, and we'll just call this positive y, and that's negative y. We'll call this positive x, and call that negative x. Make our math teachers proud, okay? So when Ginny goes 200 meters east, right, that's a no change in the y-axis, but positive 200 displacement in the x-axis. Now she goes 400 meters north. Well, that doesn't change the x-axis at all, but that's a change of positive 400. Then she goes 150 south. Again, no change there, but minus 150 south. And then she goes 175 directly southeast. How do we put that? Well, some of that displacement was east, and some of that displacement was south. Right? And if she's going directly between those, then these angles are equal and they add up to 90, and hopefully you see that this is an isosceles triangle, right? I went equal parts east and south. So those sides are equal, those angles are equal, which means they have to be 45 degrees each, right? And I can use trig to figure it out, right? So the x component is the adjacent side, and the hypotenuse is my 175 meters. I'll do it from the beginning, right? Cosine of my angle is the adjacent side, right? That's the x component, that's the y component. And when I cross multiply, you'll find that it's the magnitude again times cosine of the angle. So when I'll do that, I get 123.7. And like we said, they should be the same. Cosine was 175 times sine of 45. Cosine of 45 and sine of 45 are the same. So I get the same. Okay, so now, but the bit that was east was a positive change in the x direction. The bit that was south was a negative change. Yes, hello, Whiskers. Say hi to everyone. Yes, thank you. Alright, so those are my vectors. I'm going to add them up. Okay, so I get 323.7 meters. A net change east, it's positive, so I'm going east. And then in the north-south direction, I went south 150, and then I went south 123.7 more. But I still have a net displacement in the y direction at 126. Home stretch. Now I've got the components of my answer. Okay, so whatever Ginny's final displacement is, she went all over the place. But at the end of the day, she ended up 323.7 meters east of where she started, because it's positive. And I said positive meant east. And, that's still positive. So she still ended up... Oh, that's supposed to be straight. Not to scale. She ended up 126.3 meters north of where she started. So this is her two-dimensional displacement. Right? And I can use Pythagorean theorem to add them, right? And then we'll look at the angle. So 347. All right, 3237, 1263. Okay, and now let's look at the angle. Okay, so this angle would be my compass, right? If that's due north, we could do that. I have my triangle set up here. I don't care. We could do this one, right? Let's find out how north of due east we are. Why not? Okay, so I'll use tangent again. Right, 126 is my opposite side. 323 is my adjacent side. Right, I'll take inverse tangent of both sides. And I could have used sine or cosine. I had all three sides. I could have used whatever. I did. The hypotenuse was an extra step of work for me, so it's like one more chance for me to have goofed something up. So 21.3. We'll say 21 degrees north of due east. What I'd like to look at next is problem set 4. Okay, because I'm still grading them. I'm going to get them back to you, but at least you'll have a key that you could look at here. This is something we would have went over in class. Okay, an example of an object that's at rest but still experiences acceleration. The ones that I've graded, you've done a very good job. An object thrown up at the peak of its trajectory, right? It's still accelerating. It's accelerating downwards due to gravity. It's a free fall problem, but for that very brief instant at the peak, it's got no velocity. So a lot of things where their they're changing direction, right? The acceleration brought them to a stop, and now is going to speed them up in the other direction. There's acceleration, but for that turnaround point, there's no velocity. An example of an object that's moving with a speed of 5 meters per second, but has an acceleration less than that. Could be it's moving 5 meters per second, but it has an acceleration of 4 meters per second squared. And the point of this question is to really drive home that they're different things. Velocity is how the object is moving, and acceleration is the rate at which that's changing. But I can move to the left while accelerating to the right. I'll just be slowing down. I could move up while accelerating up. I'm just speeding upwards. If I'm moving at a constant speed, I might have a constant speed of 5 meters per second, but if the velocity is not changing, acceleration is 0. So I saw a lot of that in the ones I've graded so far. An example of an object that's moving to the left but experiencing no force to the left. We're doing a good job on this one too. An object at constant speed, right? I'm cruising to the left at a constant speed. I'm moving there, but there's no acceleration in that direction, no forces in that direction. Or if I'm moving to the left but slowing down, when we did lab 6, that guy ran out and slid across the pond. I don't know if it's from your perspective, right? He was moving to the left, but the only force in the horizontal direction was friction, and that pointed to the right, opposite of his motion. So good examples for that one. An example of an object which experiences a normal force greater than its weight. The example I gave for people that came out to extra help was you jumping on a trampoline, right? The trampoline's throwing you upwards, right? That's a surface-like thing, right? It's pushing on you, and it's obviously greater than your weight because you're accelerating upwards. If you were in an elevator, accelerating upwards too, right? If standing on a scale in an elevator, right? Your free body diagram, something like that. If I'm accelerating upwards, this has to be bigger than weight. Otherwise, the forces are balanced and I don't accelerate. So anything like that is fair game. Number 5, a 10-kilogram rubber block is pulled horizontally across the speed of ice. Calculate the force of friction. Well, we have I reset it. Wrong button. We have a formula for the force of friction, right? And since we're moving, it's kinetic, okay? And we're moving horizontally. There's not even vertical motion, let alone vertical acceleration. So when I look at my free body diagram here, okay, there's a tension pulling and a force resisting. They must be equal because otherwise I'd accelerate, and they must be equal, otherwise I'd accelerate. The way we'd write it is, the sum of the forces in the y direction's got to be 0, and that's my positive minus my negative. Now I kind of proved that they're equal. They won't always be, as we just saw above. What if, you're accelerating upwards? What if you're sitting there and your kid brother jumps on your shoulders? Now, the ground's still holding you up. It's holding you and your brother up, okay, but your weight didn't change. So it won't always be true. But here, for this rubber block, at this moment, the normal force is equal to the weight. So I could plug that in. Right, do I have a number for the coefficient of friction? Well, actually, I do. Rubber on ice. I go to my reference table there. I got rubber on ice. And it's kinetic, which is good because that's what we're looking at, 0.15. And then mg, right, is the weight. We said the normal force was equal to mg, so I got 0.15 times my 10 kilograms times my 10 meters per second squared, on Earth anyway, 15 newtons of friction. What physical thing do these slopes represent? Well, we played around with this a little bit in Lab 5, right? F equals ma. We graphed those quantities and we saw that the slope related to the way we graphed it was the reciprocal of the mass. But and even in our motion graphs, right? We saw that if the thing that was running was, slope is rise over run. If the thing that was running was position or displacement, and the thing that was that's rise. If the thing that's rising is displacement and the thing that's running is time, well, slope is displacement over time then. And we know that displacement over time is the velocity. So we've already encountered slopes having physical things. But let's look at this, right? I got friction force and normal force. And on a graph, right, that's my y-axis thing. I got a slope times the thing on the x-axis. Well, I happen to have a physics formula that says that the friction force is equal to mu Fn. Well, friction's my thing on the y-axis, and normal force is my thing on the x-axis, which means the thing being multiplied there, right, the slope is the coefficients of friction. Both the plotted lines represent single object on a particular surface. One line represents the force needed to move the object at a constant velocity, okay? And the other line represents the minimum force required to move the object from rest. Okay, so we just said the slopes are the coefficients. Hopefully you see here that one of the slopes is the coefficient of static friction, right? And one of the slopes is kinetic friction. Hopefully you see that kinetic friction is the one that is us moving at a constant velocity, right? Relative motion, we're sliding. And then static friction, of course, it's at rest, and you've got to overcome it to get it to move. The other bit you need here is that we established that the static friction is always greater. Right? And if you ever forget that, look at your reference table, right? Look at these. The static coefficients are always greater than the kinetic one. So the greater coefficient, since we just said the coefficients were the slopes, the greater the slope, the steeper the line, the greater the coefficient. So this must be the static friction, and this must be the kinetic. Use the plotted data and your knowledge of physics, as well as references found. Right? That's a good little hint there, to identify the material. So we talked a little bit in class about how why is that little annotation coming up here? Yes, that's great. Go away. Stop. Eh. Claire, where'd I go? Boom, boom, boom. We just established that the slopes were the coefficients, and in class we discussed about how, because the coefficient of friction is kind of a description of, the interactions between two surfaces, you can identify surfaces using that, and that's actually what we're going to do here. So let's find the slope, right? If the slope equals the coefficient, and I have a number for the coefficient, I can look it up on this table, right? Why does that happen when I go into pen mode? Do you see that little annotation? That's great. I know it's a chart. Thank you very much. Super helpful. Alright, so what I like to do when I find slopes is I like to find nice, pretty spots that are easy to read off of. And technically, we shouldn't use the data points. We should use the trend line, but we won't be picky here. This one... Okay. You should be able to read, right? Because it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they are tenths. So that's 7. So that point is 5, 3.7. Okay, and then down here, that'd be 0.9, 0.8, 0.75, 1.75. Okay. The slope, which for this line happens to be, the coefficient of static friction, is rise over run. You probably learned it like that, y2 minus y1 over x2 over x1. So I get 3.7 minus 0.75 over. And just to be clear here, so this is 3.7 newtons minus 0.75 newtons. So newtons in the numerator, and 5 newtons minus 1 newton, newtons in the denominator, newtons over newtons cancel out, which is what we'd expect for a coefficient of friction. .73, 0.7375. Okay, so that's our coefficient of static friction. Our coefficient of kinetic friction will be this 9. That one's kind of, right? 2.1, 2.2, 2.3, 2.4. I can't read these. It's on the screen, but I could zoom in, but then I'll have to zoom back out, and that's just annoying. You take your time. You do it well, better than I am. So it's 1.1. What is that? 1.15. Let's run with it. Let's see what we get. So y2 minus y1 over x2 minus x1. That's a 4. 0.625. And now I have coefficients. Let's go see what matches this. Alright, so a static of so steel is 0.74. That's pretty close. The nearest other thing is rubber on asphalt, which is a little higher. For kinetic, I mean steel is 0.57. That's a little lower than what I found. Rubber on asphalt is closer there. And then obviously, it depends on how well you read off the dots. And truth be told, if you did all this work and you found slopes using, good faith reading of the lines, and you give me a reasonable combination of materials, you'll be okay. Okay. When I wrote this problem, I did write it for steel on steel, so I must have. This is a little higher than. I guess maybe I'm off by a tenth when I read those a little bit, but maybe that's not 0.15. Maybe that wasn't fair, but the process is you use the slopes to find the coefficients, and you make a reasonable match to the coefficients. Both plotted line. Oh, we just did that. Okay. A wooden crate sits on the floor of a flatbed truck, initially at rest. The coefficient of static friction between the crate and the floor is 0.25. The driver of the truck wants to accelerate to a velocity of 20 meters per second within 4 seconds. Draw a free body diagram for the crate while it's on the truck. So, truck. It's a pretty good drawing of a truck, right? Crate. Right? The truck wants to drive. But we're doing a free body diagram for the crate. Gravity. And normal force. Otherwise, it would accelerate into the bed. And then there's a friction force. Now, let's look at this, right? To the crate's perspective, right, the truck bed is going to move this way. The crate thinks it's moving that way, right? So when the friction force bogs up this potential motion. Right? Remember, the friction comes from imperfections in between the surfaces, right? The friction is going to drag the crate with us, right? The relative motion is the box. Would be in a frictionless world, the box would be heading to the left. So friction is actually going to be to the right. And that freaked a lot of students out because it's like friction causing something to move. But think about why, if you've ever seen something in the bed of a truck move with the truck, what's holding it? Right? You ever see people standing on parade floats, right? They're not bolted down. Why in a frictionless world, right? The parade float should go and they should just plunk, drop underneath, because unless there's a force on them, Newton's first law of motion says their motion's not going to change, right? So it's when the parade float moves, when the truck moves, when the relative motion between the surfaces, friction's going to combat that. So it's actually friction that would carry this crate with it, and it will be to the right. The unbalanced forces have to be in the same direction the truck moves. Otherwise, there's no way the crate would move with the truck. So that was a little backwards for people, but remember, motion is relative, and in the first week of school we talked about, to the person on the train, the station goes by, and to the person on the station, the train goes by, but in the opposite direction. It's that idea of relative motion here. This is the free body diagram. Will the crate slide off the back of the truck? Okay. So the strategy here is to see how much acceleration friction can tolerate, and then compare that to the truck, right? Which that part's easy, right? The truck's going to have a change in velocity over time, right? The driver wants to go from rest to 20 meters per second over 4 seconds. So the truck would like to accelerate at 5 meters per second squared. So if we can this unbalanced force accelerate it at that rate? If so, friction will carry it with it, and if not, there'll be slippage. So Now we look at the crate. Okay, we want to know how much acceleration friction can deliver. So since friction's in the horizontal direction, let's sum up the forces in the horizontal direction. We know the sum of the forces is, the net force. Okay, according to Newton's second law, the net force is ma. Okay, and now here, the way we find some of the forces is the positive forces minus the negative forces, where there is only one force. It happens to be in our positive direction. Otherwise, we pick up a minus sign. But that's it. So friction is the net force. So the friction's equal to ma. But we know another way to calculate friction. Let's invoke that. And it's static friction, so I'll use the static coefficient. We do this in physics all the time. You have two ways to think about something. There's friction, the force, and then there's friction, the coefficient times the normal force. You have two ways to think of something, and then you can set them equal to each other. Right? We'll pull this trick over and over and over. In order to proceed, I need to come up with something. I'm at a standstill here. I don't have a number for normal force. I have a mass. I have a coefficient. I'd love to know the acceleration. Right? So when I started with the direction where my answer ought to live, the horizontal dimension, I get to a point where I don't know how to proceed. Now I look at the other dimension, and shouldn't be terribly surprised to find that normal force lives there. Well, when I sum up the forces in the y direction, they also sum up to 0. There's no acceleration vertically. There's not even motion vertically. Okay, so whatever these forces are in the vertical direction, there happens to only be 2 here. They must sum up to 0. And I can see that, yes, again, this time, not always, the normal force is equal to the weight. Now I'll plug that in. And the mass cancels. Alright, I find that my acceleration is my coefficient times acceleration due to gravity, which is 0.25 times 10 meters per second squared. And I find that the acceleration due to friction is 2.5 meters per second squared, which of course is, less than what we needed for it to not slip. So it will slip in. Alright, package sits in an elevator on a bathroom scale. When the elevator's at rest, the scale reads 20 newtons. Well, when I step on a scale and I'm at rest, the scale matches my weight. That's the weight of the package. The elevator begins to move upwards. I go from not moving to moving upwards. I'm accelerating upwards. As it moves, the bathroom scale hits a peak reading of 24 newtons, but then settles back down where it stays until the elevator begins to slow. Draw a free body diagram for the elevator while the scale is at that peak reading of 24. Okay. Well, actually, that should read the package. That shouldn't read the elevator. That's what's interesting here. Okay, weight is down, normal force is up. I drew that one bigger because I know it has to be, right? First of all, I'm accelerating upwards. Okay. Second of all, yes, Whiskers. Second of all, I already am told that the scale is reading higher than it normally would when it was at rest, right? So that's how I draw that. Okay. So there's my free body diagram. Now my peak acceleration, if I want to relate forces to acceleration, I do Newton's second law, right? F equals ma, but not just any old F equals ma, okay? But there's multiple forces at play here. Let's sum them up. The positive force minus the negative force, okay, is the net force is ma. Okay? And no, I cannot cancel masses here because I'd have to divide that by mass 2. Right? If you do that, you have to also do that division there. So we're not going to do that. Okay? But what I will do is I will solve for Well, I am going to solve for acceleration, so I am going to divide the mass over. Ignore those squiggles, okay? But the mass doesn't cancel. That's the point I'm making. So I get acceleration equals the normal force, which this is while the scale reads 24 newtons, minus the original weight all over the mass. So if while I'm accelerating the scale spiked, I have its reading. And I have the original weight. Okay? All over the mass, which if my weight, right, my normal weight is 20 newtons, it's because I must be 2 kilograms of mass. And I get 4 newtons divided by 2, you should get 2 meters per second squared. Why does the scale settle back down to 20 even though the elevator is still moving up? Well, it's moving, it's just no longer accelerating, right? The scale spikes while I accelerate, but then once I reach my cruising velocity, once I stop accelerating, once I'm at constant velocity, those are equal again. Right? And guess what? When the elevator begins to slow, I'll be accelerating downward. I'll be decelerating. And the scale will read less than my weight. And then once I come to a stop and I'm back in equilibrium, it'll read my weight again. The last thing I want to do, and then I'll wrap up this video, is I have another question here. Now, I full disclosure, I wrote this tonight, just thinking that you guys might want more practice. So if there's some proofreading that needs to happen, we can do that. All right. And if I don't get perfectly reasonable numbers, please, cut me some slack. Okay. But this will help you prepare for Friday as well. Okay. I want to kind of just let you guys do it first. But, pause your video, try it, and then here's your key, okay? Don't just watch me do it, okay? That's like singing along with the radio. It's easy to sing the words when the radio's playing. And on Friday, you're going to find out how well you really know the words. So please try it first, okay? But this is what we can do when you're done. You can come back and review this, okay? So let's get started. 70 kilogram students jumping on a trampoline. The trampoline provides an average force of 3,000 newtons as it throws the student upwards. It takes 0.15 seconds for the student's feet to leave the trampoline after changing direction. And so the downwards, they land, they come to a stop, and then it throws them up. So that 0.15 seconds, that's like from the bottom of the trampoline to when it throws them. So that's how long it takes to throw them up. How fast is the student moving when they leave the trampoline? Okay? Let's think about this. Okay, I have something about forces. I have, a duration is a kinematics variable. How fast I move when I leave the trampoline, we can think of as like a final velocity if we're looking at while the trampoline throws me. Okay, so I could do a chart. Let's do a chart. You probably don't need a chart for this, but when in doubt, do a chart. And let's do, wall, trampoline, throws. Okay, so this is, you gotta figure, I'm gonna go from my turnaround point to when I'm back up into the air. So at my turnaround point, I'm actually at 0 meters per second, and that's what that time is for. It's from the turnaround point to being back in the air. I'm trying to find my final velocity at the end of the throw. Okay, and my acceleration, it's not gravity. Don't you put -10 there. I'm not going anywhere upwards if my acceleration is -10. This is where the forces are going to come in. Okay? Because I know that the sum of the forces is the net force, and the net force is ma, right? So that's my net acceleration. Alright, so what forces are on this? Well, I've got the trampoline upwards. I'll just call that the 3,000 newtons. But I also got my weight downwards. Okay? So I got the trampoline's upward throw minus, if I'm 70 kilograms times 10, right? Weight is mg, so that's my 70 kilograms times 10 meters per second squared. So that's my 700 newtons equals, I'll divide m over. Right, and then mass is my 70 kilograms, so got my 3,000 newtons minus my 700 newton weight, that's the net force, divided by my 70 kilograms. So the trampoline throws me with an acceleration of 32.8 meters per second squared. And that's what goes here. So now I have my three kinematics variables, right? And I can use this guy, Vf equals Vi plus At. And that one's 0. Right? And A is my 32 meters per second squared for my 0.15 seconds. My final velocity as I leave the trampoline is 4.9 meters per second upwards. Got it. How high above the trampoline is the student 0.3 seconds after being thrown? Okay, let's do a new chart, because this is a different section of motion. This is from being thrown to 0.3 seconds later. So time is 0.3 seconds. I just found my initial velocity. We just said they throw me with 4.9 meters per second. Okay. And I want to know how high I am that time later. Now, I need one more variable. The moment I leave the trampoline, I am in free fall. While the trampoline's throwing me upwards, I'm at a high positive acceleration. That's why I accelerate up. But the moment my feet leave, I start to slow down. The moment my feet leave, I'm in free fall. So there are my three. Okay, I can use this one. This is the one that has the three things I have and the thing I need. So I've got my 4.9 meters per second times my 0.3 seconds plus 1/2 times, this is acceleration to gravity, times my 0.3 seconds squared. Move the around so I can see. So I got 4.9 times 0.3, and calculators no order of operations, but I like to do parentheses just to make myself feel better about it. Times 0.3. When in doubt, more parentheses. So VIT plus 1/2 AT squared. 1.02 meters. At 0.3 seconds after leaving the trampoline, so at this very same time, the student suffers a mid-air judo kick from a roughhousing friend. The kick is horizontal, right, and gives the jumping students a horizontal, I don't know, I gotta take the S out, a horizontal velocity of 3 meters per second. What is the magnitude and direction of the student's velocity at this time? Okay. Well, they're still moving vertically, but now they're also moving horizontally. Okay, so now this is a side view. Okay, let's figure out how much they're moving vertically, and we can complete this little triangle here. Okay, so now I want to know that. Okay, I can do something like VF equals VI plus AT, right? Because then I can find out if I started off at 4.9 meters per second, 0.3 seconds later, how much have I slowed down? So that's actually negative. So 4.9, minus AT. So that 10 times 0.3 is 3. So I'm at 1.9 meters per second. So and that was positive. So I'm still moving upwards at 1.9 meters per second. But now I'm also moving at 3 meters per second to the right. Okay. The boat is moving across the river, but the current's taking it down the river, and I need to find the total velocity. It's Pythagorean theorem. A squared plus B squared equals C squared. .55 meters per second. That's its two-dimensional speed. Okay, let's find an angle, right? Above the horizontals, a cool one, which will actually be equal to that angle. When two parallel lines are cut by a transversal, opposite interior angles are congruent. Do you guys know that one yet? Doesn't matter. I mean, you can see it here too, right? Isn't this, 90 minus theta? And isn't this 90 minus theta, right? So if these two have to add up to 90, and these two have to add up to 90, then those two must be the same. So it's kind of another way to think about it. Okay, but either way, I've got my 3, I've got my 1.9, and, I'm going to find that angle. But whatever angle you pick, it will be fine as long as you tell me what I'm looking at there. So my opposite side is my 1.9, my adjacent side is 3. .32 degrees. So if that's 32 degrees, then that's 90 minus 32, which means that's 90 minus 90 minus 32, which will end up being 32. 32 degrees above the horizontal. Kick. What is the maximum height of the student? Okay, the horizontal kick isn't going to play into effect here, right? This is a vertical, that didn't, because it was horizontal, it didn't affect the vertical trajectory at all. So I can just go right back to a vertical height. Let's do from thrown to peak. Okay, I know that I left the trampoline with 4.9 meters per second velocity. At my peak, I'll have 0. I'm looking for how high I went, and I know my acceleration is free fall. Alright? So I can do something like the one that doesn't have time in it. I'd love to find delta y. Okay, the final velocity is 0, so I'm going to subtract that over. I get negative vi squared over 2a equals delta y. So I got negative, that's my 4.9 squared, right, all over 2 all over negative 10. 1.2 meters. So he was almost at the peak, but he got judo kicked. Okay. The edge of the trampoline. I'm going to need my numbers, that's why I'm not clear in this. The edge of the trampoline is 2.5 meters away from where the student was jumping. Will the judo kick send them off the trampoline? Okay. So how can we figure this out? I might actually have to clear this out to make room, which is unfortunate, but that's okay. Okay. So I just found out that I was a certain height above. Let's draw. Maybe a picture will be good. Okay. So I have my trampoline, okay, and the edge is 2.5 meters away, big trampoline, okay, and I'm falling, and I've now been judo kicked to the side horizontally, and it's the only source of horizontal velocity. Okay, so the question is, will my horizontal velocity, how far will I displace in the time it takes to fall? Okay, we didn't do anything with time yet. Okay, you could probably do this using the heights. I'm going to do this with time. I'm going to go back to the vertical direction, and I'm going to find out how much longer he had to fall. Actually, I think he was still moving up, so he's going to go up and then fall. Because once I have that time, that flight time, I know that my horizontal displacement over time, I know that. Right, I know that's the 3 meters per second I gained on the kick. I'm seeing if that's bigger than 2.5 meters. So I really need that. So I'm going to go back to the vertical direction here, because the vertical direction is really what determines the flight time, right? The flight is over when you're back on the ground. It's a vertical question. So let's do this then. Let's go back to it's not the ground we're talking about, it's the trampoline. Well, during this whole bit, I'm going to go from throw to land, really back at the trampoline, okay? But what I'm saying is I want to know, when do I return to my original height, okay? Because I know he was, right, 0.3 seconds in when he got kicked, and I want to know how far he's going to travel sideways during the rest of that. So if I could find the whole time, I could subtract off my 0.3 seconds, and I could find out how long he's moving sideways for. So I want the time, okay? And in order to find the entire time, that's when, I start off at y equals 0, and I want to know when I'm back at y equals 0. So that's why I got 0 displacement. From throw to land, in the vertical direction, there's no forces except gravity. Yeah, he gets judo kicked, but that's horizontal. Okay? And I need one more to get started here, but I actually happen to know that I took off at 4.9 meters per second. The equation that has all that I need here is this one. And before you get, but keep in mind I have 0 displacement here, so I won't have to do quadratic equation. Okay, I'm going to solve for t. Okay, when I subtract this over, I get to this point, and here t cancels, not completely, but one of them on the right cancels with the one on the left. There's only one t left in the equation now, and I can solve for it. I'm going to multiply 2 over and divide a. So I get t equals negative 2 vi over a. Alright. Headset's making a run for it. And I'm going to get, so t is negative 2 over negative 10, and vi was 4.9. So the 2 over 10 cancel, the negatives cancel. I get 0.98 seconds. So that's the total flight time, right? The kick didn't affect the vertical direction, right? So I will be back at my original height. I will be back at trampoline height 0.98 seconds after I left. The kick happened 0.3 seconds into this. Right, so he's traveling sideways for 0.68 seconds. Right, how far is he going to get in 0.68 seconds? Well, that's when this comes in. I want to know how far he's going to get. The kick gave him a 3 meter per second bump. Right, and he flew for 0.68 seconds. Right, there's my 0.68. 2.04. So he will travel sideways 2.04 meters. He's not going to get thrown off the trampoline. No fictional characters were harmed in the making of this physics problem. Okay, you gotta be safe when you're on a trampoline. Okay, but also you gotta keep track of what variables you have and what section of motion you're looking at. Okay. Question 2. A mad scientist builds a machine that flings ice cubes across tables at ridiculous speeds. Just because he's weird. The device applies a 10 Newton force to an ice cube at an angle of 30 degrees above the horizontal. The coefficient of friction between the ice cube and the table is 0.15. What is the acceleration of the ice cube while the device applies force? Okay? So hopefully you believe me that this force will make this thing move. That's a kinetic. If you look at your table, that's a kinetic friction. It wasn't like that other problem where it was, potentially there was a friction force, a static friction force that wouldn't even let it move. It's gonna move. Okay. Plus, it tells us it flings at its ridiculous speed, so we know it moves. Let's just run with kinetic friction here. When I do a free body diagram, okay, I have an applied force, right? That's 30 degrees. Okay, of course the ice cube has weight. Okay, normal force. There's going to be a frictional force that opposes it. Okay. You know what? Let's just proceed. Let's go ahead. Okay, a mad scientist. What's the acceleration of the ice cube while it is? So let's find the net. The motion's horizontally. Okay, let's find the net force in the x direction. So I'm going to sum up the forces in the x direction, and that's the net force in the x direction. My x direction, I have the, how do I want to do this? I'll do FA. Right? Okay, that's okay. That's okay. Right? I have the x component of the applied force is in the positive direction, right? And friction's going to subtract that, and it's going to be equal to MA. The friction, actually, I think I needed to give you. You remember that the ice cubes are 2 grams. I'll add that in before I publish this out to you guys. Okay. I could probably do an expression for anyway, but I won't do that to you. Okay. So I can solve for my acceleration right there, and I'll use my friction is mu times Fn. Okay, Fn is not the weight here. Okay. There's 3 forces in the vertical direction. There's the normal force up, but there's a downward portion to that applied force too. Okay. And when I look at this applied force, I want to know how much is horizontal and how much is vertical. Right? That's my 30 degrees. That's my 10 newtons. Okay? How much is horizontal? Well, that's the opposite side. So it'll be sine force applied in the y direction. Right? And I cross multiply. Okay? And that means the force applied in the x direction is the hypotenuse times cosine of 30. So when I go to look here and I need my normal force, and I'm going to sum up the forces in the vertical direction, which do sum to 0. The normal force is the positive force. Then I have my, that points down, my 10 times sine of 30. That's the vertical component of the applied force. And of course, weight is also down. So I'm going to add them back over, and I'm going to see that the normal force is equal to them being added together. Which I can actually get a number for. Ready? So it's 5 newtons of that 10 is down, plus the weight, which at 2 kilograms is, 2 grams is 0.002, right? 1, 2, 3, but times 10. 5.02 is the normal force. 02 newtons. So my friction force is my 0.15 times my normal force. .753. Okay, back to my horizontal dimension, right? I now have a number for that, I have a number for that, I have a number for that. The acceleration is the x component of the applied force minus the friction, right? That's the net force in that direction minus the mass. So I've got my 10 cosine 30, right? Because this, what I just wrote there, that's the x component of the force minus my friction force, which I just found, all over my mass of 0.002, right? 1, 2, 3 kilograms. Acceleration is malformed expression. What did I do wrong? Oh, that goes outside the 3,953 meters per second squared. Hey, the problem told you it was ridiculous. Okay, so that's my acceleration. How fast is the ice cube moving if it takes the device 1 millisecond to fire? So this incredible acceleration is going to exist for 1 millisecond. Okay, so I have an acceleration, but I also know that that's my change in velocity over time, right? So if I have my acceleration times time, I get my increase in speed. So I'm going to take this big old number and multiply. So there's my 3, 9, that's my acceleration. And I multiply by 1 millisecond, which is 1 times 10 to the 3rd seconds. Times, right? 1 times 10 to the negative 3rd. Oh, I need to use that. 3.95. Now 3.95 meters per second isn't that bad. Now a millisecond's pretty quick. Don't get me wrong. Okay, but here's a demonstration of how even a big acceleration, if it's for a really, really small period of time, then that's the velocity that I got. See what you got. How far would the ice cube slide before coming to rest? So there's my initial velocity. Okay. The situation is going to change a little bit, but let's get this on the board. Okay. 3.95 meters per second is how fast they come out. This is from launch to rest, right? Because I'm going to slide to a stop. I want to know how far that happens. And the question is, what's the acceleration? It's not that super big acceleration, right? As soon as this thing leaves the device, the applied force is gone. This becomes my free body diagram. Okay, normal force is dropped, right? These are the only two forces vertically, and they still add up to 0, so now they're equal. Okay, and friction is the only player here, which means when I look at the x direction, right, that's the only x force. And it's in the negative direction, so I'm doing negative. Equals ma. Okay? but I also know that that's mu times the normal force, which hopefully C is mg. Don't need mass for this bit. Okay. The acceleration is my 0.15 coefficient times 10 meters per second squared of gravity. So I get negative 1.5 meters per second squared. And it's negative because it's going to slow down, right? If that's a positive velocity, I'd expect a negative acceleration if it's going to ever slow to a stop. Alright, the one that doesn't have time in it is that. I'm solving for that. Hey, that's 0. So I'll subtract him over. Negative vi squared over 2a equals delta x. 3.95, right? 3.95 meters per second. That'll get squared over 2 times negative 1.5. So we'll square that. We'll make it negative. Divide by 2. Divided by negative 1.5. It'll go 5.2 meters. Okay. So, which, still like 30 feet. But, yes. Okay. So if you have any questions about that and about like evaluating your answer, I know we got to talk about it a little bit, which is a good habit. Okay, but I'm writing these. they sometimes they have silly answers. I work really hard though to try to make them realistic. Okay, and that's a good habit to check your answer for reasonableness. But start folding some physics stuff into that too, right? Don't just think like that's pretty fast for an ice cube. Start thinking like, should this be negative? Should this be bigger than the weight? Should this be smaller than the weight? Like, let's fold that sort of logic into our error checking too. Okay, so I'll post this extra question. Hopefully you know that already, because hopefully you tried it before you watch that. Otherwise, it's a big old waste of time. But you've got everything you need here to do good on this. I want you to email me if you have questions. I know that I'm back in editing mode. That's why I'm changing that. I won't be in the classroom tomorrow, but I'll have my phone, I'll try to check my emails as often as possible, and you just let me know what you need, okay? And then if you happen to be section 5, I'll see you on Thursday for lab. We can go over more of this stuff, and you will be ready to roll on Friday, alright? Good night, take care, and I'll see you all soon.